All right, well, hey everybody. I'm broadcasting live from my house in this green screen studio that I set up. Um, Very long story how I managed to do it, but you gotta do what you gotta do. Um, I'm going to talk about the midterm 2 review. There is some new content that I want to discuss in this lecture before we get into that, and it's more fun than it is sort of like here's exactly what's going to be on the midterm. So let's go ahead and jump into that. So
If you just give it a little push, it just sits there and tumbles end over end. It's not a very stable platform.
So this is, I'm going to turn the volume down here. So this is a video from the International Space Station, and they have what's called a compact disc player, CD player. I don't know if you've heard of these things. But inside of this thing, there's a little disc. It spins around, obviously. And what's interesting is that when the electric motor inside of it starts to turn the disc, well, then the total momentum is still conserved. And so one of the things that you notice at the beginning of this video is that he's going to press play. So right now it's not spinning, right? But in a minute he's going to press play, and you'll notice how it starts to go in a particular direction. Yeah, do you see how it starts to turn and then he has to kind of like stop it? When you're stopping it, that's an external torque, okay? So that's changing the total angular momentum of the system. But now that it's spinning, what's interesting is that it stabilizes it in some way. So it still kind of wiggles. It's not perfectly stable, but it's a lot more stable than it would be if the disc weren't spinning inside. And so this is the idea behind frisbees, even bicycles. So one of the things as a kid that is so tricky about learning to ride a bicycle is that it's not stable until you're actually moving at some speed. And so it has to do with this, what's called gyroscopic motion. Same thing with tops. Tops are overall surprisingly stable if you kind of flick them or whatever. So this is what I would call gyroscopic motion. If you want to see the whole video, you can click that link there if you want. Now, there's 2 CD players. By the way, astronauts get like 2 personal items when they go into space. And a nice choice is a CD player, by the way. And so this astronaut has borrowed CD players from fellow astronauts, and now he's taping it together. And what he's doing is he's pointing out that if you have 2 of them that both have discs that are spinning in it, right now the discs are not spinning, it's just sort of flopping around or whatever. But if you start both of those discs spinning, then it's a much more stable platform. So I think it's spinning now, and now he's going to nudge it. There we go. And you see how much more stable that is? Not perfectly stable, but it's certainly a lot better than it was. And so this is kind of gyroscopic motion that I'm going to talk about in just a second. Before I do, he's going to add a 3rd CD player to this thing and get that one spinning up. And the reason that he's doing this is because satellites that are in orbit, the way that they orient themselves is with gyroscopes. So it's not that there's a satellite and they have like a little puff of thrust to get it to turn this way and a puff of thrust to get it to stop. You'd run out of fuel pretty quickly if that was your approach. So instead what they're doing is, each satellite has gyroscopes. So often when you hear about repair missions to the Hubble Space Telescope, things like that, a lot of times they're trying to fix the gyroscopes because there's like 6 gyroscopes on the Hubble Space Telescope. 6, not 3, but 6, because keeping that thing stable is incredibly important. And so if one of those gyroscopes goes down, they have to have at least 3 or 4 to be able to operate the telescope. So in any case, gyroscopic motion. How does this happen? I'll tell you about that in a second. The next thing I want to show you is this, which is, so this is a person sitting on kind of a rotating platform here. It's all greased up so it can spin around. And there's a bicycle tire. And if you're doing this and you're trying to turn the bicycle tire complete 180 degrees. So initially it looks like this, and you're just sitting there. But if you try to turn it all the way around to the other way, you find that you start spinning like crazy. And by the way, this is all at slow motion video capture, so it's a little bit more subtle. But you'll notice that once the thing is 180 degrees, he doesn't stop spinning. He keeps on spinning like this. And I'll talk about why that happens in just a second. But yeah, he's continuing to spin around like this. Okay. So what's happening here? Well, here's how I would explain it. So initially, when that bicycle wheel is spinning, initially there's a total angular momentum that is, I guess down, I suppose. There's some total angular momentum. I think in the next example, I'm assuming that it's up. So up like that, whatever, one way or the other. So there's some total angular momentum here because the wheel is spinning, the person is not. But if you try to flip that over on a frictionless thing, greased up thing, well, total angular momentum is still conserved. So if you start like this, and you're going to flip it over to that, well, the wheel is going to be spinning in the opposite direction, right? So the wheel is spinning like this, but now it's going to have the opposite angular momentum, but total angular momentum is still conserved. And so this angular momentum and that angular momentum had better be equal to each other. And by the way, there's also the angular momentum of you sitting on the platform, the spinning platform. And so this is why you start spinning, is that the total angular momentum is conserved, but this thing is going the opposite way. And so therefore you have to start spinning because of that. And so we can actually do a calculation. We can use this to figure out how fast you should be spinning. The gyroscope is spinning. It has its rotational inertia. You have your rotational inertia and your spin rate. So we can do something like this. So here's my rotation, our rotational inertia, our spin rate. Exactly what this rotational inertia is for us is a little hard to say. The rotational inertia for the gyroscope is a little easier. You can use that hoop equation where all the mass is at the end, all the mass is at the same radius away from axis of rotation. So if those two things are the same, and if this is true, then, right, so this is true, then the following is true, which is that. So your angular momentum is twice the initial angular momentum of the gyroscope. And so you can use that to try to figure out what your spin rate would be. Again, we don't know exactly what your rotational inertia is, but if we did, we could try to figure out what your spin rate would be. It would go from being 0 to this. Okay? So that's kind of interesting application of that. Now, there's a subtle thing here that it's worth pointing out. And again, I'm not going to make a big deal about this on the midterm, but I think it's worth pointing out, which is that what about halfway in between? What about when the wheel is halfway, kind of in the middle here? Not so that it's spinning this way, not so it's spinning that way, but what about when it's sort of in the middle, here? Let's think about this in terms of angular momentum conservation, okay? So we know that the initial is like this, and, initially this is 0, so I think that's going to get scratched out there, yep. The final is like this, so this is non-zero, this is non-zero. This is equal to that, right? But in the middle, if you think about it, one of these two things has to be non-zero, right? Because this thing is spinning, so now you're holding the thing like this, and it's spinning like this, and so the angular momentum is that way. So it's probably going to have, one of these is going to be non-zero, probably the y, which is a little weird because there's no way that this can be equal to that. There's no way that this can be equal to that, right? So it's almost as if the total angular momentum isn't conserved, which is a little crazy. Why would it not be conserved? Well, it is conserved, but there's another rule that I haven't told you yet, which is that when you are applying a torque to these things, so if you're just sitting there, then that's fine. If you're just sitting there, then your angular momentum here had better be equal to angular momentum here. By the time you get the thing over here, you're just holding it. You're not trying to twist it. Okay, but if you are trying to twist it, then the angular momentum does strange and unexpected things. So I think I just said this. So the answer is that if you have some, we talked about this last lecture, if there's some torque here, that can change the angular momentum vector. But it takes torque. You have to twist this thing. And it is because of this thing, which is why this doesn't add up. But in the end, it does. It's just that in this middle stage, because you're changing the angular momentum of the gyroscope, you're applying a torque, it does. Again, the key is that here, the thing that makes this different is that if you can just do this experiment, if I could send you all a bicycle wheel in the mail, your arms will be moving. You can feel your muscles sort of trying to twist this thing in the middle, whereas once you get it to the end, it's just sort of holding it there, holding it up. Again, in the beginning, you're just holding it up. But here, it takes effort to try to twist the thing. And ultimately, that's why this doesn't really work so well. Anyway, long story short, applied torque is the key. Okay. If you want to know more about rotational motion, maybe even a little more than is absolutely needed for this course, Walter Lewin has a great lecture on rotational motion. There's also OpenStack's textbook. One of the semesters I taught this course, we used OpenStack's. It's a pretty good textbook, not as good as the textbook that you guys pay for, but if you want a bunch of other example problems and insights, you can check that